In this video, I want to talk about calculating the equilibrium distribution of the two more stable chair conformations of a substituted cyclohexane. I'm going to start with methyl cyclohexane. And we know the axial methyl group here is less stable than the equatorial methyl group. Because of the 1,3 diaxial interactions between the methyl group on carbon 1 and two axial hydrogens on carbon 3 and carbon 5, which would become equatorial hydrogens on the equatorial substituent. Since we're focused on the methyl substituent, I'm not going to draw all of the hydrogens in here. So we know that this equilibrium lies to the right, and I'm drawing it with the equatorial substituent in the chair conformation on the product side and the axial in the chair conformation on the reactant side, which is the opposite of what the table in the textbook does, so that I will be working with negative delta G of reaction. And for this one, delta G of reaction is minus 1.75 kilocalories per mole. And the reason I'm doing that is it will be more convenient in the calculations to work with equilibrium constants. And by having a negative delta G, I ensure that in my calculation I'll have a positive exponent inside the exponential, and thus a greater equilibrium constant greater than 1. So if I want to figure out what the equilibrium distribution of these two chairs is, I can use the fact that I know that because of that large difference in energy between even the twist boat forms and the chair conformers, right, where the chair conformers are more stable than the twist boat by about 5.5 kilocalories per mole, and more stable by the boat than the boat by about 6.9 kilocalories per mole. Effectively, the two chair conformations are the only conformations that we'll see. So we can add up the total amount of concentration of chair 1 and the concentration of chair 2, and we can say that that's going to be equal to 1. Or 100% of the molecule will be in one of these two chairs. That's actually not true for some of the larger substituents where delta G here is becoming on the order of the same magnitude as the difference between the twist boat or the boat and the chair conformation, but it's legitimate for most of the examples that we're going to be looking at. So now all I need is I need the equilibrium constant, because the equilibrium constant for this reaction is defined as the concentration of chair 2, the equatorial methyl, divided by the concentration of chair 1, the axial methyl. And I can calculate the equilibrium constant by using the fact that I know that delta G is equal to minus RT, natural log of the equilibrium constant, which in rearranged form says that the equilibrium constant is equal to E to the minus delta P0 over RT. So I can set this equilibrium constant, chair 2 over chair 1, equatorial over axial, equal to E to the minus 1.75 kilocalories per mole. And as always, I'm going to want to change it into joules because I know R is joules, that's 8.314 joules per mole Kelvin. So I'll multiply this by 1,000 calories over 1 kilocalorie, and by 4.184 joules over 1 calorie. And then in the denominator, 8.314 joules per mole Kelvin times 298 kelvin, the standard thermodynamic temperature. And if I plug those numbers into the calculator, the two minus signs will cancel. And I come up with E to the 2.955 and an equilibrium constant, AQ, of 19.2. Yeah. So concentration of 2 divided by the concentration of 1 is 19.2, and the concentration of 2 is equal to 19.2 times the concentration of 1. And I can now plug in 19.2 times 1 for 2. Actually use all the significance. So 20.2 times the concentration of chair 1 is equal to 1.00, and the concentration of chair 1 is equal to 1.00 over 20.2. Is equal to 0.049, or approximately 4.9%. Which means that this one is 95.1%, or 19.2 times the concentration. Got it. So even an energy difference of 1.75 kilocalories per mole gives us a roughly 95:5 ratio of the methyl group in the equatorial position versus the methyl group in the axial position. You can do the same calculation for any of the other substituents. And you could actually do the calculation kind of in reverse to find out how big an energy difference you would need to get to eventually a conformationally locked rate, right? Get a 99.9%, 0.1% ratio, which we would say is effectively all in the equatorial position. What would you need for your delta G0? We know that 5 kilocalories per mole is enough, because we say that the T-butyl group, which is 5 kilocalories per mole difference, is conformationally locked. But what about the isopropyl group? Is that effectively conformationally locked? Does that reach 99.9% at 2.2 kilocalories per mole difference? How would we go about doing this calculation? Well, now we know that equilibrium constant K2 is equal to 99.9 over 0.1, or 999. And that's equal to the concentration of the equatorial divided by the concentration of the axial substituent. So I can use delta G 0 equals minus R T ln K dQ, and I can plug in my equilibrium constant of 999 and calculate the delta G that would result. If I do that, delta G0 is equal to minus 8.314 joules per mole Kelvin times 298 Kelvin times 1 calorie over 4.184 joules times 1 kilocalorie over 1,000 calories times the natural law of the equilibrium constant, which is 999. Kelvin cancels, joules cancels, calories cancels, and I end up with units of kilocalories per mole. So let's plug those numbers in. Take 999, take the natural log. That's actually 6.91. And I calculate delta G0 of 4.10 if I round. 4.1 if I round. 4.09 if I don't round. anytime I have an equilibrium constant, or sorry, anytime I have a delta G0, a free energy difference between my two conformers of 4.1 kilocalories per mole or greater, I will have 99.9% or more of my more stable equatorial conformation. The isopropyl group is only 2.2 kilocalories per mole, so I have not achieved the 99.9% to 0.1% distribution there. In many cases, you can add up the energy of the energy cost of putting a methyl group in the axial position, which in this case cost us 1.57 kilocalories per mole, and the energy cost of putting the other substituent in the axial position. In this 1,4,4 methyl cyclohexane, where both the fluoride and the methyl group are at the top face, giving us a cis arrangement, there are two possible chair conformations, one of which has the methyl group in the axial position and the fluoride in the equatorial position, and the other which has the fluoride in the axial position and the methyl group in the equatorial position. But it only costs me 0.25 kilocalories per mole with that fluoride in the axial position. Right? So the total cost in this one is 0.25 kilocalories per mole, whereas the total cost in this one is 1.75 kilocalories per mole. I can now calculate delta G0 of reaction by taking the strain cost, the cost of putting the fluoride in the axial position of plus 0.25 kilocalories per mole, and subtracting from it the cost of putting a methyl group, and discover that the free energy change for switching from the axial methyl equatorial fluoride to the axial fluoride equatorial methyl would be negative 1.5 kilocalories per mole. This would be more stable than this one by 1.5 kilocalories per mole. And I can do that because the fluoride and the methyl group are on opposite sides of the ring, so they're not actually interacting with each other in either conformation. They're only interacting with the other axial hydrogens. The hydrogens on carbon 2 and 4 in the case of the cis, the chair with the methyl group in the axial position, and the hydrogens on carbons 3 and 5 in the case of the chair with the fluoride in the axial position. It's not always possible to simply add up the two numbers from the table, though, because in the cases where the two substituents on the ring are either adjacent to each other or separated by one CH2 group in between, you will find that the substituents do interact with each other in one or both of the chair conformations. So though it is true that the difference between trans 1,4-dimethyl cyclohexane in the conformation that puts both methyl groups axial and the alternative chair that puts both methyl groups in equatorial positions is exactly twice the 1.75 kilocalories per mole, or the delta G0 of approximately, 1.70 for methyl, 1.75 is methyl, where delta G0 is minus 3.40 kilocalories per mole. I think I used 1.75 for methyl in the previous calculation, I meant methyl. So delta G0 is minus 3.4 kilocalories per mole, since you're relieving 1.70 kilocalories per mole of strain energy by putting this methyl group equatorial and another 1.70 kilocalories per mole by putting the other methyl in the equatorial position. If you work with the corresponding trans 1,2-dimethyl, however, you discover that although the one that puts the two methyl groups in the equatorial position is more stable, it is not more stable by 3.40 kilocalories per mole. And the reason for that is because in this chair conformer, these two methyl groups are in adjacent positions. There is actually a 60-degree dihedral angle between them. Which results in a gauche torsional strain. And we know that a gauche torsional strain between two methyl groups has an energy cost of 0.9 kilocalories per mole. It's worth pointing out that that energy difference, that energy cost of 0.9 kilocalories per mole, is a strain energy, which is more comparable to an enthalpy than it is to a free energy, whereas this 3.4 kilocalories per mole is based on the numbers from the table in chapter 4, is a real free energy. So it's not quite accurate, but it's close to accurate. So in this case, we have 1.70 kilocalories per mole energy cost for putting that methyl group axial, and 1.70 kilocalories per mole energy cost for putting this methyl axial. Both of those are relieved, but we end up with a strain of 0.9 kilocalories per mole in the product. So the difference between the two can be calculated the same way we calculated the 4-methyl 1-fluoro derivative as 0.9 kilocalories per mole minus 3.4 kilocalories per mole. Or delta G0 is equal to minus 2.5 kilocalories per mole. So we're switching from the diaxial methyl 1,2-dimethyl cyclohexane to the diequatorial 1,2-dimethyl cyclohexane. We lose only 2.5 kilocalories per mole of energy rather than 3.4 kilocalories per mole of energy. It might be productive, since it's a little difficult to see that there's a gauche interaction there, to write this cyclohexane as a Newman projection instead. When you look at a cyclohexane as a Newman projection, you'll notice that you're always going to be looking down two carbon-carbon bonds at the same time. So if I look down this carbon-carbon bond as a Newman projection, I'm also looking down the carbon-carbon bond on the other side. And both of these are in their fully staggered conformation. If I have a chair cyclohexane, you can see that these two orange groups, which are the methyl groups, are 60 degrees apart in a gauche position. So how do I show that? Well, I'm going to look down two carbon-carbon bonds at the same time. And I'm actually going to look down this carbon-carbon bond and this carbon-carbon bond. So I'm looking down that carbon-carbon bond and that carbon-carbon bond. So if I number this, I want to look down the carbon 2,1 bond, and I want to look down the carbon 4,5 bond. So I'm going to draw my Newman projection, two adjacent circles, so that carbon 2 here is in the front, and carbon 4 is also in the front. Connecting the two front carbons is the bridge with carbon 3, and that's pointing up. Connecting the back carbon, which is carbon 5 here and carbon 1 here, is a bridge where they're both pointing down. I can then put the other positions in so that I have 120-degree dihedral angles between the adjacent bonds on the same carbon. And off carbon 1, which is the back carbon, I have a CH3 group in the axial position pointing straight up. And off carbon 2, which is the front carbon, I have a CH3 group pointing straight down. And then off carbon 4, all I have is hydrogens. So this is the Newman projection that corresponds to the chair with the two methyl groups axial with a 180-degree dihedral angle. And you can actually see the 1,3 diaxial strain for the methyl groups quite clearly, both on the top and the bottom, between carbon 2 methyl and carbon 4 hydrogen, and between carbon 1 methyl and carbon 5. And you could look down the other bonds if you wanted to see the interaction between carbon 1 and carbon 3. So now I need to draw the other chair, or the other Newman projection, for the molecule on the right. The difference will be that now the bridging, sorry about that, I highlighted the carbon 3, 4 instead of the carbon 5, 4. So I need to be looking down carbon 2 to carbon 1 and carbon 4 to carbon 5. Now the bridging carbon 3 is pointing down. So when I draw that Newman projection, I'll start with my two circles, but off the front carbons, the front bridge is down instead of up. Which means off the back carbons, the bridge is the other way. My methyl groups now are in the equatorial positions, and my hydrogens are in the axial positions. So I no longer have, right, I have the methyl group on the top of the ring pointing up on carbon 1, and on the bottom of the ring pointing down on carbon 2, but those positions are now in equatorial instead of in the axial positions. So I no longer have these 1,3 diaxial strains, but I do have this gauche strain. This 0.9 kilocalorie per mole of the two adjacent equatorial methyls causes the chair conformer on the right to be a little less favorable relative to the 1,4 dimethyl situation. If I look at cis 1,3 dimethyl cyclohexane, I see a different situation. Where the two methyls are in the axial position here versus the equatorial position, this is strain free. There are no gauche interactions. The two methyl groups are in the equatorial positions, and they're pointing far enough away from each other that it's the same energy as if they were in the 1,4 positions. But now I have an interaction in a 1,3 diaxial sense of two methyl groups. So I can't just add up the 1.7 kilocalories per mole that this methyl group would cost and the 1.7 kilocalories per mole that that methyl would cost. Right? That would be a methyl group interacting with two axial hydrogens, but that's not what I have here. what I have here is a methyl group interacting with an axial hydrogen and then also interacting with another axial methyl group. So if I look at the interactions with this hydrogen, the one methyl group is interacting with the hydrogen, so there's a 1,3-diaxial CH3. And this other methyl group is interacting with that hydrogen. So there's also a 1,3-diaxial hydrogen CH3 here. But now there's a 1,3-diaxial CH3 as well. I know how much a 1,3-diaxial CH3 hydrogen interaction costs. It's half of the cost of putting one of the methyl groups in the axial position, or half of 1.7. So this is costing us 0.85 kilocalories per mole. And this one is also costing us 0.85 kilocalories per mole. It turns out that the energy difference between these two, delta G0 for this reaction, is negative 5.4 kilocalories per mole. I don't know how much this strain costs, but I know that the total strain of the left-hand molecule is equal to 0.85 kilocalories per mole plus 0.85 kilocalories per mole plus X, where X is the cost of putting the two methyl groups in an axial position relative to each other. And I know that the sum of X plus 0.85 plus 0.85, or X plus 1.7 kilocalories per mole, is equal to negative 5.4 kilocalories per mole. That enables me to determine that the cost of putting these two methyl groups axial relative to each other is 3.7 kilocalories per mole. So by moving this methyl group into the equatorial position, I'm relieving the 0.85 kilocalories per mole strain that it's having with the hydrogen on carbon 5, but I'm also relieving 3.7 kilocalories per mole strain that it has interacting with the methyl group on carbon 3. And by putting the methyl group in carbon 3, I'm also reducing the 1,3-diaxial strain that it's having with the interaction with hydrogen on carbon 5. So the net is the sum of those three unfavorable interactions and a total of minus 5.4 kilocalories per mole. That's greater than the 4 kilocalories per mole that we calculated to give us a 99.9% to a 0.1% ratio. So this rate is essentially conformationally locked. The effect of putting two methyl groups both in the equatorial position versus in an axial position interacting with each other is slightly larger than the effect of putting a single TU group in an axial position. So you have to be a little bit careful. You can use the numbers in the table in an additive fashion, but only if there are no gauche interactions between them, which you'll see if they're on carbon 1 and carbon 2 respectively, and there are no 1,3-diaxial interactions between substituents as opposed to between a substituent and a hydrogen, which you'll see when you have a cis arrangement in a 1,3